Temperature and the Zeroth law of thermodynamics. In this session, we will explore several key topics related to thermal physics. We begin with the Zeroth law of thermodynamics, which provides the logical foundation for the concept of temperature. From there, we will define what it means for objects to be in thermal equilibrium and how temperature acts as the deciding factor in that state. We will also examine how thermometers function by utilizing various physical properties of materials. Finally, we will discuss the practical application of these concepts through the Celsius temperature scale. The Zeroth law of thermodynamics states that if two objects, let us call them A and B, are separately in thermal equilibrium with a third object, C, then A and B are also in thermal equilibrium with each other. This law is essential because it allows us to identify a shared property among these objects, which we define as temperature. The diagram shows object C, a thermometer, measuring objects A and B to have the same reading of 22.5 degrees. Because both are in equilibrium with the thermometer, they are in equilibrium with each other. This means that if we were to place A and B in direct contact, no energy would be exchanged between them because they are already at the same temperature. Understanding temperature requires looking at how energy moves between objects. Temperature is the property that determines whether energy will transfer between two objects when they are placed in thermal contact. If two objects have different temperatures, energy will transfer from one to the other. This flow of energy continues until the objects reach the same temperature, a state known as thermal equilibrium. It is important to note that temperature is an intrinsic property. This means it is independent of the size, mass, material, or density of the objects involved. Only the temperature itself dictates the direction of energy flow. Let us test our understanding with a quick quiz. Imagine two objects with different sizes, different masses, and different temperatures are placed in thermal contact. In which direction does the energy travel? Option A suggests it moves from the larger object to the smaller one. Option B suggests it moves from the object with more mass to the one with less mass. However, based on what we just learned, the correct answer is C. Energy always travels from the object at a higher temperature to the object at a lower temperature, regardless of their physical size or mass. Thermometers are tools used to measure temperature by monitoring specific physical properties that change in a predictable way as temperature fluctuates. Many different properties can be used for this purpose. For instance, we can measure the change in volume of a liquid or the change in dimensions of a solid. In gases, we can look at the pressure of a gas held at a constant volume or the volume of a gas held at a constant pressure. Other methods include measuring the electric resistance of a conductor or even observing the change in color of an object as it heats up. Each of these properties provides a measurable way to quantify thermal changes. Common liquid thermometers, like the ones shown here, typically use a mass of mercury or alcohol contained within a glass capillary tube. When a thermometer is heated, the liquid expands, which causes the column to rise and increase in length. The image shows a thermometer in a liquid bath where the level has risen to 30 degrees Celsius. In these devices, we define the change in temperature as being directly proportional to the change in the length of the liquid column. This allows us to create a linear scale for daily temperature measurements, though the range is limited by the freezing and boiling points of the liquid used. The Celsius temperature scale is built using two specific calibration points at standard atmospheric pressure. The first is the ice point, which is defined as 0 degrees Celsius. This is the temperature at which a mixture of water and ice exists in thermal equilibrium. The second is the steam point, defined as 100 degrees Celsius, where water and steam are in thermal equilibrium. To complete the scale, the interval between these 2 points is divided into 100 equal segments. Each of these segments represents exactly 1 Celsius degree of temperature change. While liquid thermometers are useful, they have significant limitations. Different liquids, such as mercury and alcohol, have different thermal expansion properties. This means that even if both thermometers are calibrated perfectly at 0 and 100 degrees, their readings might not agree exactly at an intermediate temperature like 50 degrees. Additionally, these thermometers have a limited functional range. Mercury freezes at -39 degrees Celsius, making it useless in extreme cold, while alcohol boils at 85 degrees Celsius, limiting its use for high heat. To achieve high accuracy, scientists need a more universal scale that does not depend on the specific material being used. A constant volume gas thermometer offers a more universal approach to measuring temperature. This device exploits the fact that the pressure of a gas varies with temperature when its volume is kept constant. As shown in the diagram, a gas-filled flask is immersed in the environment to be measured. To ensure the volume remains constant, the mercury reservoir, labeled B, is adjusted up or down until the mercury level in column A returns to the 0 mark. The difference in height, labeled H, between the two mercury columns allows us to calculate the gas pressure. Because different gases behave very similarly at low pressures, this method provides a much more consistent standard than liquid-based thermometers. To summarize the main points of this lecture, we have learned that the Zeroth law of thermodynamics defines temperature as the fundamental condition for thermal equilibrium. We established that thermal equilibrium is reached when there is no net exchange of energy between objects in contact. We also reviewed the Celsius scale, which is anchored by the ice point at 0 degrees and the steam point at 100 degrees for water. Finally, we noted that gas thermometers are preferred for scientific standards because they offer a more universal measurement that is less dependent on the specific substance inside the device. We conclude with 2 review questions to reinforce these concepts. First, if object A is in equilibrium with object C, and object B is also in equilibrium with object C, what can we conclude about the energy exchange between A and B if they are touched? Based on the Zeroth law, they are in equilibrium with each other, so no energy will be exchanged. Second, why might a mercury thermometer and an alcohol thermometer show different readings at 50 degrees Celsius, even if both were calibrated correctly at the ice and steam points? This happens because the two liquids expand at different rates, highlighting the need for more universal measurement standards.